Welcome to The Explainer. Look, if you are trying to seriously level up your scientific toolkit, you are in exactly the right place. Today, we're taking a massive leap in our physics journey, and we're going to discover together how to move from abstract math straight into visual reality. I mean, think about it for a second. Up to this point, you've probably been doing a whole lot of number crunching. And maybe, just maybe, you felt that little twinge of math anxiety wondering, well, what happens when just plugging numbers into a formula isn't enough anymore? Because trust me, as physics problems get more complicated, that wall, it's coming. But hey, don't sweat it. Today, we're totally moving beyond simple number crunching. We're going to learn how to actually visualize the problem, turning all those confusing numbers into clear, simple diagrams that honestly practically solve themselves. Okay, let's dive into this. Here is our roadmap for mastering one-dimensional vectors today. First, beyond just crunching numbers. 2, scalars versus vectors. 3, rules for drawing vectors. 4, adding vectors in 1D. And 5, subtracting vectors, with a little twist at the end.
All right, kicking things off with Section 1, beyond just crunching numbers.
As we start shifting toward those heavier, more complex problems, drawing a vector diagram isn't just some nice, colorful way of listing your givens, it's a strictly necessary step. Mastering these diagrams is absolutely crucial to your success in pretty much all the physics courses you're ever going to take. Why? Well, because when we use these diagrams, we're creating a picture that truly represents the actual physical motion of an object. We are literally translating reality right onto the page.
Moving on to Section 2, scalars versus vectors.
To actually draw reality, we need to understand our building blocks. Pretty much anything you measure in physics is going to fall into one of two categories. Scalars, they're super simple. They're just a single number representing magnitude, and that's it. But vectors? Vectors are a measurement given as a number and a direction. You'll usually see that direction written inside square brackets. Oh, and here's a huge pro tip for the rest of our work. Whenever you see an arrow drawn in a physics diagram, that arrow literally is a vector. The terms are completely interchangeable.
Next up, Section 3, rules for drawing vectors. So, while we use vector diagrams for all sorts of things, the rulebook for drawing them is strict but very simple. First, the arrow has got to point in the vector's direction. Second, the length is proportional to the magnitude. So, a 20 km/h vector, it must be drawn exactly twice as big as a 10 km/h one. Third, you can pick up and move a vector anywhere on the page as long as its size and direction don't change. And finally, to add them together, they absolutely must connect head to tail.
So, the crucial point is this: direction is everything. If an object is moving east, you better make sure that the arrow points east. It's the defining feature of what makes a vector, well, a vector. Never forget to include that direction in your square brackets.
Okay, let's slow it down a bit for Section 4, adding vectors in 1D.
When you're adding what we call collinear vectors, vectors that line up right with each other, it's a super straightforward three-step process. First, you mentally or even physically on your paper pick up that second vector. Step 2, you've got to make absolutely sure it stays the exact same size and points in the exact same direction, no changing it. And Step 3, you plunk it back down so that the vectors connect head to tail. Basically, the pointy tip, the head, of the first vector has to touch the blank end, the tail, of the second vector. Once you've got your original vectors connected head to tail, you need your final answer. In physics, we call this the resultant. The resultant is the sum total of two or more vectors added together. And here's exactly how you draw it. You start at the very beginning, the tail of your first vector, and you draw a line finishing exactly at the end, the head of your final vector. Because of this, the resultant is the only line in your entire diagram that touches tail to tail at the start and head to head at the finish.
Actually, let's inject a little fun here with a classic Pac-Man analogy. Imagine your original vectors A and B show the path Pac-Man is moving. Starting at the tail of A, Pac-Man chomps his way to the right. Then he hits vector B and continues chomping a little more to the right. So what's the resultant? It just shows that overall, Pac-Man has moved to the right a whole bunch. He could follow the individual paths of A and B, or he could just follow that one resultant arrow and end up in the exact same place.
Let's visualize this with some real distances. Imagine you plan to walk 4 kilometers east along vector A. Then you decide, hey, I'm going to walk another 6 kilometers east along vector B. Your resultant, your final end destination, is simply 10 kilometers east. Let's move to the next slide and see how this builds. What if we completely reverse the journey? Let's say you walked the 6 kilometers east first along vector B, and then walked the 4 kilometers east along vector A. Your resultant? It's exactly the same, 10 kilometers east.
And this right here proves a fundamental rule for adding one-dimensional vectors. The order simply does not matter. Vector A plus vector B gives you the exact same result as vector B plus vector A.
And finally, section 5, subtracting vectors. This is where we get to the twist.
Now, what's really interesting about this is that often in physics you actually have to subtract vectors, like when you're finding a change in velocity. But here is the plot twist. We don't actually have to learn a whole new set of drawing rules. Nope. Instead, we take a subtraction problem like a minus b, and we literally just turn it into an addition problem, a plus negative b.
Here is the critical secret to this whole concept. In physics, a negative sign isn't some math operation telling you to take something away. Not at all. A negative sign simply means in the opposite direction. So, if we want to subtract vector b, all we do is take the original vector for b, spin it around a full 180 degrees so it points in the exact opposite direction, and then boom, we just add it head to tail exactly like we did before.
Let's bring Pac-Man back to really anchor this. Say vector A shows Pac-Man moving to the right a whole lot, but vector B is negative, meaning he turned around 180 degrees and moved back to the left a bit. What's the overall outcome? Well, the resultant shows that, from his starting position, he only made a pretty small move to the right.
Which brings us to our final and honestly vital puzzle to leave you with. We proved earlier that when adding, a plus b equals b plus a, but does a minus b equal b minus a? I want you to really think about it. If you spin vector b around 180 degrees, it points one way. But if you spin vector a around 180 degrees instead, the whole diagram completely changes. Subtraction is absolutely not commutative. The order matters immensely. So figuring out exactly how those different diagrams look, well, that is the absolute perfect challenge for your next physics problem set. Keep visualizing, keep drawing those arrows, and I promise you will never be stuck just crunching numbers again.